All right, so let's talk a little bit about vector valued functions. And we're going to start kind of by comparing them to what we had before with our parametric curve. So before I had x equals and a y equals, and these are both functions of time. So I could call this like f of t and then perhaps g of t. And for example, this might have been x equals 2t, and then y might have been cosine of t. And I had these two parametric curves that together put together a single curve with an x and y position that was a function of time. That was our parameter. So we're going to take a look then at vector value functions and how they sort of compare, which is to say that really in two dimensions with a single parameter, as we will work with them this year, these are really kind of the same thing. And they're just notated differently. So a position vector, we might note, let's make sure we have our pen here, as r of t, and we'll put this little like half arrow over top of the r to know that this is a position vector. And this is going to be equal to our x function, if you will, f of t, and we might write like a little I hat afterwards, plus g of t, j hat, or a little j afterwards. Instead of dotting those with an I, we'll dot them with a little hat to note that these guys really don't have any sort of value to them other than they are showing us that these mini functions, right, that are functions of time, sort of are corresponding to f of t and g of t in the x direction and in the y direction. You might also see this written as r of t. And again, we'll put this little half arrow over top of the r of t equals, and you might see with the angle brackets, f of t, comma, g of t. And so we have this same sort of idea that we had before, where we have an x position and a y position defined, but now we have these defined and sort of written differently. And there's some different, as we go through this chapter, you'll see some different applications for parametric curves, which typically sort of deal with things in a relational sense, maybe graphically, something that kind of spirals around and does something funky, versus things in function form uh, that might sort of be applied that way. The the vector value functions have more of a speed and uh, distance, velocity, acceleration sort of relationship, where we think of these parametric curves as being more sort of a graphical kind of application. So let's take a look at just one of these and what this looks like. We'll switch, we'll go back to blue. So if I have r of t equals, and we'll use the angle bracket notation. The AP folks seem to like that one. We just do 3t squared plus 7. And so that's my x function for my x position. And then we'll make it trig sine of 2t will be our y position. So this puts together a sort of similar to a parametric curve, right, with an x and a y sort of function, if you will. And we could consider a position at any time. We could say, okay, well, what's the position r of 0? And the position is an xy position at time 0. And in this case, that position would be 7, comma, well, sine of 0 is 0. And we could continue that for any different time that we wanted to. We could plot that the same way we would plot a parametric curve, where at a particular time we'd have an x position and a y position, and we could kind of get a graph for what that function looked like. Now, we can also apply a little bit of calculus to this, and this is actually pretty simple, because if you want to know the velocity vector, v of t, you simply take the derivative of your x, in this case 6t, and the derivative of your y separately. So how about 2 cosine, little chain rule, of 2t. And now you could find the velocity at any given time in the x direction and in the y direction. right? You can find the velocity. It would be really easy to find it at 0. So at a given position, 7, 0, you could say that, switch of color, that the velocity at that particular time is 0, comma, 2 times cosine of 0 would be 2 times 1, 0, 2. So at that particular position, 7, 0, our particle or whatever is moving around here is really only moving vertically, right? Because our x velocity is 0. You could go a step further if you wanted to. We'll change one more time, and we can find the acceleration vector as a function of time. And our acceleration vector would be 6, comma, well, we need another derivative. How about negative 4 sine of keeping inside the same 2t? And you could talk about the acceleration. Notice that the acceleration for this particular function would be constant in the x direction. We have a constant x acceleration while we have a variable acceleration in the y direction, right? As this thing changes from positive to negative and positive to negative as sign changes. So you have simply a different way of writing these things, these vector value functions, but still have an x and a y component function, an x component function and a y component function that kind of kick this off. You could write all of these in your I and j notation if you wanted to. So give a little bit of space here and we'll see if we can get these in here. So it would be, r of t. Oh, I don't like that r. R of t could be written as 3t squared plus 7, throw that in parentheses, I plus sine of 2t j, I hat and j hat. And again, these little guys just kind of serve as placeholders. They don't have any real value here, but they just sort of say this is going to be our x direction, this is going to be our y direction. And so we kind of can distinguish, very similar to what we have here with the angle brackets, just two different ways to notate this. So again, you can imagine that your calculus is pretty straightforward if the derivatives work this way. And we'll talk in later videos or perhaps in class about how we can work backwards from acceleration given some initial information. Maybe it's some velocity information or some position information. And we can take the antiderivative to work back from an acceleration vector to a velocity vector and then to a position vector. So that's a little bit of an intro about the vector value functions and how they compare to our parametric curves very similarly with the two component functions, and how we can apply just a little bit of calculus just along the x vector and the y vector, or the x component function and the y component function.